Hello, I'm Laura Marshall.
And I'm Melinda Rose, and this is Light Matters for February 20th, 2013.
On this week's show, space rocks rock Earth, a probe emits light in living cells, X-ray lasers reveal a photosynthesis catalyst, and we learn about a new camera system from imec.
There was much discussion in the last week about a large asteroid called 2012 DA14 passing super close to the Earth, but it was totally upstaged by a meteor that landed in Russia with a force of 500 kilotons. The Russia meteor, the largest reported since 1908, is believed to have been about 55 feet long and weighed 10,000 tons before hitting our atmosphere. The trajectory of the meteor was significantly different than that of asteroid 2012 DA14, which hours later made its flyby of Earth rather quietly. Lucky for us, it stayed well outside our atmosphere, but it was still inside our belt of satellites in geostationary orbit, which is about 22,000 miles above Earth. Meteors routinely hit the Earth, but these recent events have renewed discussions about developing systems to deflect or even destroy such threats. Two California scientists propose using the sun's energy to vaporize large space rocks. Philip Lubin and Gary Hughes conceived D-STAR, or Directed Energy Solar Targeting of Asteroids and Exploration. A directed energy orbital defense system, D-STAR is designed to harness some of the power of the sun and convert it into a massive phased array of laser beams that can destroy or evaporate asteroids posing a potential threat to Earth. It could change an asteroid's orbit, deflecting it away from Earth or into the sun, and could also be used to assess an asteroid's composition. They say all the basic elements for the system pretty much exist today, just not at the required scale. Lubin and Hughes have calculated the requirements and possibilities for D-STAR systems of several sizes, ranging from a desktop device to one measuring 6 miles in diameter. Also, a University of Hawaii team is using a $5 million NASA grant to develop ATLAS, the Asteroid Terrestrial Impact Last Alert System. ATLAS will operate up to 8 small telescopes, each equipped with cameras of up to 100 megapixels, to patrol the visible sky twice a night looking for faint objects moving through space. The team predicts the system, expected to be fully operational by the end of 2015, will offer a 1-week warning for a 50-yard diameter asteroid or city killer and 3 weeks for a 150-yard diameter county killer. ATLAS will complement the Institute for Astronomy's Pan-STARRS project, a system that searches for such asteroids years, decades, and even centuries before impact with Earth. For information on a ground-based laser system for dealing with near-Earth objects, our Photonics in Space webinar features Dr. Alexander Rabanchek of Lawrence Livermore National Laboratory speaking on the promise of pulse lasers in removing orbital debris. It's available on demand at photonics.com/webinars or by clicking the link in this video.
A new class of light-emitting probes small enough to be injected into individual cells could provide new ways of exploring cell dynamics. Stanford University engineers are the first to demonstrate that sophisticated light resonators can be inserted inside cells without damaging them. Their nano device focuses and amplifies light using quantum dots and photonic cavities. At the cellular level, nanobeams act like a needle that harmlessly penetrates cell walls, emitting light upon insertion. While other investigators have shown that it is possible to insert simple nanotubes and electrical nanowires into cells, no one has yet realized such complicated optical components inside biological cells. The most immediate use for the nanobeams would be in the real-time sensing of specific proteins. The studied cells in this case came from a prostate tumor, making cancer research another possible application. The engineers loaded the nanobeams into cells and watched as the cells grew, migrated, and reproduced. Each time one divided, one of the daughter cells inherited the nanobeam from the parent, and the beam continued to function as expected. This enables researchers to study living cells longer, something not possible with existing detection techniques, which require that cells be either dead or fixed in place. The probe is described in nano letters.
A couple of months ago, we brought you a story of how X-ray lasers were being used to map the parasites that cause sleeping sickness, a step toward creating a cure. In a new study, a team using the X-ray laser at the SLAC National Accelerator Laboratory combined the X-ray laser's ability to determine the structure of fragile protein crystals without damaging them with X-ray emission spectroscopy to probe both the geometry and electronic structure of a sample. They used the laser to simultaneously look at the structure and chemical behavior of a natural catalyst involved in photosynthesis for the first time. The work at SLAC's LINAC coherent light source is a breakthrough in studying atomic scale transformations in photosynthesis and other biological and industrial processes that depend on catalysts, which efficiently speed up reactions. Catalysts are vital to many industrial processes, such as the production of fuels, food, pharmaceuticals, and fertilizers, and represent a $12 billion per year market in the U.S. alone. The research appears in Science Express.
The Belgium-based research group imec recently introduced a new hyperspectral imager for snapshot and video acquisition, and they showed it at Photonics West this year. Melinda spoke with Vision Systems team leader Andy Lambrecht about it.
Yes, for the first time we are showing to the public our hyperspectral snapshot camera, in which we have integrated our spectral filters directly on top of the CMOS image sensor. In this case, we have subdivided the sensor into 32 separate zones, and every zone sees the same view of the world, which gives us multispectral or hyperspectral imaging at video rates. So when I spin this wheel, you see that the different zones of the sensor, each seeing very specific, different narrow banded color, see the same image. And then when we overlay those images on top of each other, we can use 32 bands of spectral information to do real-time classification at video rates. So what you see here now is when we overlay the 32 bands on top of each other, we can do a false color image of the scene we see, and based on the spectrum, every pixel in the image is classified into a different class. And this all can happen at video rates.
So last year when I was here at Photonics West, I talked to you about another imaging system that you had, which can you give us an update on that? That's ready to be commercialized?
Yes, so last year we presented here at Photonics West our hyperspectral line scan solution based on the same technology, also with integrated spectral filters on top of the image sensor. And over the last years we really matured that system so that people can now take an evaluation system and start developing their application based on this technology to validate the application. So we've put together a kit which is very user-friendly. People can be up and running in half a day, and it has a computer, a hyperspectral camera, line scan, stage, frame, and calibrated lights, and everything you need to validate your application.
Great, well thank you very much. imec was in the North Hall at Photonics West with many other exhibitors from Europe, and the traffic seemed steady in that hall throughout the entire show.
Yeah, you know, according to SPIE, attendance was up more than 2% from last year to 20,737 attendees. So it seems it is still the place to meet and do business.
I know I had a lot of great conversations with people, and you did as well, and you'll be seeing some of those in the weeks to come at the end of this broadcast. Until then, that's it for this edition of Light Matters, Photonics Media's weekly newscast.
Write to us with your comments or questions at lightmatters@photonics.com.
Thanks for watching, and we'll see you next week.